So number 1, you should have gotten 1. Number 2, you should have gotten 5. 3 was x to the 2/3, and 4 was x minus 1, all raised to the 2/3 plus 1. Now again, if you had like 2/3, you could have had it written as like the cube root with a square inside. But remember, if you're finding a function composition of a number, you get a number. If you're finding function composition of a variable, your answer should have a variable. And that is always true for function composition. So if you're composing functions with variables, you'll get a variable. If you're composing functions with numbers, you'll get a number. Okay, in 5 is hinting on what we were supposed to cover in 1.4, which is parametrics. So what they wanted you to do in 5 was to say that the variable was equal to the letter t, and then replace all the x's with t's. That's kind of why we skip 1.4. Unless we are doing parametric derivatives, there's not a true use for it, so you could have skipped 5 and 6, sorry. I meant to cover them. Okay, 7 through 10. In 7, the two curves would intersect at the point 4, 5. In 8, the two curves intersect at 8/3 and -3. So again, 2 ways you could have done that. Put it in your graphing calculator and find the point of intersection. Or algebraically, you could have replaced -3 with y here and solved for x. In 9, they intersect at 1.58, 3, and they intersect nowhere for part B. In 10, they intersect at -1.39, 4, and in part B, they intersect nowhere. And then I just kind of threw this up here because we'll be using it today. Recall that a to the x equals y is the same as log base a of x equals y. So we're going to look at change of base formula today and involve some logs with our lesson. So if you had 2 to the x equals 3, that would be the same as log base 2 of x equals 3. So again, we are looking at inverses today. We're looking at logs, and then we're looking at the applications of those. So this goes back to talking about one-to-one and why we need to talk about one-to-one with inverses. A function is a rule that assigns a single value in its range to each endpoint in its domain. So a function says for every x, there is only one y. A function passes the vertical line test. A function has to pass the vertical line test. Some functions assign the same output to a different input. Parabolic curves are examples of those. X equals 2 and x equals -2 for the function x squared both give the output of 4. So some functions assign the same output to more than one input. Oh, same example. X squared assigns output 4 to both 2 and -2. Other functions never give an output a given value more than once. So there are functions like lines, where you will never get the same y value no matter what x value you plug in. A cubic function is another example of this. No matter what I plug in for x, I will never get the same y. If each output value of a function is associated with exactly one input value, then that function is said to be one-to-one. A linear and a cubic function are examples of one-to-one functions. A parabola is not one-to-one. A one-to-one function passes both the vertical and the horizontal line test. A function f of x is one-to-one on a domain D if and only if f of a never equals f of b when a does not equal b. Okay, one-to-one functions. The horizontal line test states that the graph of a one-to-one function, y equals f of x, can intersect any horizontal line at most once. If it intersects such a line more than once, it assumes the same y value more than once, and therefore cannot be one-to-one. So the example on the left of the cubic is one-to-one. The example on the right of the parabolic is not, because it fails the horizontal line test many times. Okay? Example 1. Using our horizontal line test, determine whether the functions are one-to-one. So we have f of x equals the absolute value of x, and we have g of x equals the square root of x. So go ahead right now and very quickly, below those two functions, without using your graphing calculator, sketch those two curves. So, would the absolute value graph pass the horizontal line test?
No.
No, of course not. So V, it hits many, 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 many times. Okay? So, the black curve is the square root of x. Does the square root of x pass the horizontal line test? Yes. The second piece is as if you graphed plus or minus the square root of x. Does this pass the horizontal line test?
Yeah.
There you go. So sometimes it can pass the horizontal line test, but remember, in order to be a one-to-one function, it has to first pass the vertical line test. So the example given is just to show you that, okay, yes, we could look at something like this, but it fails to even make it to being one-to-one because it's not a function. Okay. Why talk about one-to-one when I told you today is about inverses? Well, there are some properties of inverses that need an understanding of one-to-one. Since each output of a one-to-one function has only one input, a one-to-one function can be reversed so that we have an inverse to it. So what we do is we send the outputs back to the inputs and the inputs back to the outputs. So the rule is, in order to have an actual inverse function, the original function has to be 1 to 1. In order to find an inverse, the original function has to be 1 to 1, so that there is only one output and input reverse. If you think back to when we first did inverses, we used to say that the domain becomes the range, and the range becomes the domain. And in the very most basic idea of finding inverses, I gave you something like y equals x minus 2. To find its inverse, what did we tell you to do? We said flip x and y, so you had x equals y minus 2, and resolve for y, so that the inverse was y equals x plus 2. So here was your original, and here was your inverse. Any point I had on here in the domain, so let's say when x is 1, well, 1 minus 2, negative 1. On this graph here, what it means is if I put in negative 1, I should get 1, which I do. Negative 1 plus 2 is 1. The domain and the range switch places. The range becomes the domain becomes the range. That only works if it's 1 to 1. If you think about a parabola, you have the point 2, 4 and negative 2, 4. What happens if you flip the domain and range? Well, now 4, where does it map? Does it map to 2? Or does it map to negative 2? So it becomes iffy in how it maps to another point. The function defined by reversing a 1-to-1 function is known as the inverse. Composing a function with its inverse in either order, meaning Fogg or Goff, should give you the identity. You have to show both. It is not enough to show Fogg equals x. You have to show both. Okay, the next is simply just notation. The symbol for the inverse of f is f raised to the negative 1. Again, we don't call it f of negative 1, we call it f inverse. I'm not sure what unintelligent mathematician made it that, because all it does is confuse you and make you want to write it as 1 over f of x, which is not the same thing. However, that's the notation, and it's not changing anytime soon. So f of g of x equals x and g of f of x equals x means that we have them. So Fogg and Goff are equal, and they're both equal to x. Then f and g are inverses of one another. If they do not equal x, then they are not inverses. Okay, determine via composition if f of x equals the square root of x and g of x equals x squared are inverses. So we have f of g of x. So what that means is we're going to put g into f. So you have the square root of x squared. By definition, the square root of x squared is the absolute value of x. Why?
Is the plus one?
Okay. Kind of. This actually goes back to something I stressed in Algebra 2. Go ahead.
You can square like a negative number and it still gives you the same value as a positive.
Exactly. So no matter what I'm going to get out of the square root of x squared, it's got to be positive no matter what. Remember when I used to stress to you even, odd? So like if you square rooted x to the fourth, you got an even because you got x squared. So it didn't matter. But if you take the square root of x squared, that's an even exponent. 1/2, or the square root, is considered even, but this is x to the 1, therefore it's odd. Therefore you have to have absolute values. Because you could technically make this -1 for x. So you have to have those absolute values. The square root of x squared is absolute value of x always, by definition. Okay, let's look at Goff. So now we have a square root of x going into something squared. So again, the square root and the square cancel, and you get x. This is why the absolute value is so absolutely necessary. Here, what's the domain of a square root? What's the domain of this? Are these the same?
No.
So are they inverses?
No.
That's why it's so critical to understand domain, range, and the rules. This absolute value of x is not the same as x. Okay? In order to find an inverse, we're going to do the exact same thing we used to do in Algebra 2. You're going to flip x and y and solve for y. So, given that y equals 4x minus 12 is 1-to-1, which we know it is, it's linear, let's find its inverse and graph them. So, I'll graph 4x minus 12 in blue. So, y equals 4x minus 12 is my original. In order to find its inverse, I am going to flip x and y. So I'm going to get x equals 4y minus 12. I'm going to solve for y. So I have x plus 12 divided by 4. Or y inverse equals 1/4 x plus 3. Graphing each of those, start with your y-intercepts and apply your slopes.
What's that intersection like? Does that mean anything?
Like where they intersect,
Yeah.
it should just be symmetric with this line.
Doesn't have any significant value.
Not really. So, like, the idea is that if this point here is 0, 3, on the original it should be 3, 0. If this point here is 4, 4, then it should be 4, 4, which is the flip of it on this one. If this point here is -4, 2, then on this graph it should be 2, -4. But they will intersect, and typically their intersection, again, you can see, is going to be symmetric with the line y equals x. So that's why I have that dashed line up there. The dashed line, this line right here, this is called the identity line, right? This is the most basic graph. It's y equals x. Y equals x is the parent function of linear functions. It is the only function without a slope and with a y-intercept of 0. So y equals x is the parent function of linear functions. It is also the line that divides all inverses. Any function that is an inverse will be symmetric about that line. So what that means is I could fold this graph in half, and blue and red will lay on top of each other if I folded about the line y equals x. That is true for every inverse function ever. And that was actually like a bonus question I asked you. That's not, no. Remember, we move quicker. I get 2 days, or 2 periods, you know. Do you want to break now, or do you want to finish the lesson and break before homework?
No.
I can finish the lesson. I like mostly there. Okay, a base A logarithmic function. If A is any positive real number other than 1, the base A exponential function f of x equals a to the x is 1 to 1. So that's important to know because it's hard to remember, but it means that any base A to the x function is 1 to 1. And that should make sense if you think about what an exponential graph looks like. It's going to pass horizontal and vertical line tests. It therefore has an inverse, and its inverse is called the base of a logarithmic function. So a of the x has an inverse. Its inverse is the logarithmic function log a x. The base of a logarithmic function y equals log base a of x is the inverse of the exponential function y equals a of the x. So these two functions are inverses, and there is a proof, and I could show you that proof, but it is long, it is rigorous, and it's much easier for you to just remember a to the x and log base a of x are inverses. So, much like what we talked about before, the domain of log base a of x is 0 to infinity. Yesterday we said the domains of log or y equals a to the x was all reals. Well, guess what the range of log base a of x is?
It's all real.
All reals. They flip. Their properties flip. Similarly, think about the log on your graphing calculator. What does the log on your graphing calculator have? Well, it has a log base 10 automatically. You cannot change the base on your graphing calculator. So over here, when we just talked about these, we talked about the fact that this is log base A, where your graphing calculator is limited to log base 10. You can't never change the log base on your calculator, well, without changing base, but I'm saying if you hit the log key, that A is always a 10. Let's talk about how that's going to affect or come into play with its inverse. So logs with base E and base 10 are so important in applications that the calculators have special keys for them. They have their own special notation and names as well. So, y equals log base e of x is the natural log key on your calculator. So if log base e of x is the natural log key on your calculator, will we know about the inverse of natural log of x? What? Which one? You just said 2.
Well, I said something.
I know.
I said the right one.
What?
No, I'm just kidding. No, I'm just kidding.
The inverse of natural log of x?
Well,
Yeah, what is
the
it?
x? It's the blue. It's in blue, right? One above it. It's right above.
Sure,
natural log.
that is, okay. You could go with that it's in blue, but yes, it is e to the x. It wasn't meant to be a trick question. Guys, it was supposed to be
Okay.
apply the property that we just talked about. Log base a of x has an inverse of a to the x. So if it's log base e of x, its inverse is e of x. I wasn't trying to trick you.
I know. You gave me
You
a look and I
actually
was like,
said it.
wait a minute.
You
She's
said
tricking
it,
me.
and then you took it back. And I was like, okay. So log base 10 of x on your calculator, we call this the common log. It's just log of x. That means its inverse is 10 to the x. So again, special keys on our calculator. Mas importante in calculus.
I'm actually learning German right now.
I don't know how to say something's very important in French.
I took first.
You don't know how to say it either?
What?
Something's very important. How do you say something's very important? Like, mas importante is very important in Spanish.
Oh, okay.
Muy
That-
importante.
I don't know if they important. Trading is like a lot of
Yeah,
Yeah, très bien is very good. So what would très? Oh, guys, my heart is breaking for you.
Hey, we go.
All right, sorry, we went off on a language tangent. So, inverse properties. These are really just things you kind of have to memorize. A to the log base a of x is x. The a and the log base a cancel each other out, guys. Hence the identity of a to the x and log base a to the x are inverses. So if you plug one into the other, you get x. That's why you use e and natural log to cancel each other out when you're solving for x that's like locked away up in an exponent or in a log. You use e to cancel the natural log because of the fact that they're inverses and it's the identity property. Oh, I never knew that. What?
Yeah, Lacey went over a little bit. She was like, hey, look at this. I'm like, okay, now look at this.
Yeah, there you go. That's really what it was. Well, I'm saying, hey, let's look at this, because we're going to be doing this a lot.
Let's look at this and let's keep looking at it. That's
Like,
awesome.
we're going to talk about the derivative of e to the x at some point. Derivative of the natural log of x. What's 1 over x and what's e to the x? Okay. So did I put these in your notes today then?
Yes.
This is that handout I was kind of talking about, and I have another one that's even more concise, but the best way to learn something is to write something. So I'm writing. Okay. I need some enjoyment on a Wednesday. Yes. It makes you feel like I had 5th grade assignment after work last night. 3 assignments on a computer. So day 1 for him, he had 3 math assignments on a computer. I didn't give you math homework on day 1.
Yeah.
That's what I said. Day 1, he had math at work.
Remember that? He like shot Bible verses at people.
At Trinity, they have this same textbook. They take the chapter 1 test the third day school. That's disgusting.
He's like, now tell us,
I'd
like,
rather sit here and teach
in modern words what that means.
They take chapter 1 test.
And he's like, well, in the Bible it said, please test things. The father's like,
Day 5 is not so bad.
you don't say like this in the Bible.
I was stretching it. Just stretching it. All apply to LN. I think there was a time when my board was not very user friendly. So basically, meaning everywhere you have a log, you could replace log with natural log, and all of these rules are true. That's what I'm saying. Instead of making you write out all the rules for natural log also, it's, hey, everywhere you have a log, you could replace it with a natural log, and it would still be true. Almost there, guys. Change of base formula. You've seen it. We're going to live and breathe by it. Log base A of x is the natural log of x over the natural log of a. This is how you get around the fact that your calculator is stuck at log base 10. This is how you get around that problem. Memorize this. Or maybe button make it log base. What? Yeah. It's probably new. Like, is it on his? Oh, yours.
Oh. No, that's how we use it.
No, because guess what? There will be non-calculator change of base problems, and they're going to ask for the answer in terms of the natural log, and you're going to have like the natural log of 7 over the natural log of 11, and they don't care what the decimal is, but you got to know how to do this. Okay. Hence these examples where there's x's, and a calculator is kind of useless for you for a little bit. So it's the natural log of x equals 3t plus 5. Find me my x. So how do you get rid of the natural log? We just talked about it.
Oh, that change base.
No.
Before that.
The e. What is the inverse of ln? E. So we e both sides. So you have e to the natural log of x equals e to the 3t plus 5. The rule of function composition with inverses is e to the natural log of x is the identity, which is x. So you get x equals e to the 3t plus 5. That's your answer. I know, I hate t's. E to the 2x equals 10. I need to know what x is. How do I get rid of the e?
Natural.
So it's the natural log of e to the 2x equals the natural log of 10. Go back to your rules. What are the rules? If you have a natural log and an e, they
Cancel.
So 2x equals the natural log of 10. So x equals 1/2 the natural log of 10. If I told you you could only have this in terms of ln's, meaning no numbers outside it, dividing it, or etc., you could actually say this is the natural log of the square root of 10. because this can come in as a power of what's inside the parentheses. This is a very likely multiple choice question where you have to know that identity. Solve the following for x. So this goes back to like last night's homework where you'd be like, hey, in algebra 2, we just changed this to a base of 2. Can I make 12 have a base of 2? Yeah, 12 is in a perfect square of 2. So now you have to use that identity property that we just talked about. So how am I going to get x by itself when I have 2 to the x equals 12?
Log base 2.
Okay, so you could say what? Log base 2 of x equals 12. But how does that help me?
You can take log base 2 to both sides. That would bring the x down, right?
So if you take log base 2 of both sides, well, I was just going to change my base, but I guess what you do is get you there too.
So what's that, right? And the log base 2 and the 2 cancel out, right?
Yeah.
What's wrong?
I mean, if you do it this way, you then just change a base here. So you get natural log of x over natural log of 2 equals 12. So then you have natural log of x equals 12 natural log of 2. And then I just said x equals e 12 ln. So I'm trying to think if your way still works, because then my 12 came up here as a power. The e's and the ln cancel, and I get e equals 2 to the 12. Which I think you'd eventually get to the first two. I think I'm. Keep it that way. I know. I just have to think on if this works. I'll try it. And compare with this one. Yeah.
Could you go back?
That's sorry, something. Sorry.
No, but it was like I thought it was log of a, then y equals x. I thought the exponent is on the other side of the. Is it not?
No, you're right. A to the y equals x, and then it's log. Thank you. So it's gonna flip those. Oh, sorry, guys. It just, there's so many numbers you have to switch. So look, ready? It's a to the y, which I messed up because it was x. A to the y equals x, which means this should be log base a of x equals y. And then because it was an x, I wrote it in the x spot. So this should be log base 2, which is why maybe orange was on margin. And I was looking at yours going, what do you think? So that should be log base 2 of 12 equals x.
Exactly what I meant.
Well, when you said that, you said log base 2 of each side. Like you only base the sides.
Why not? We base each side that brings down the x, and then you have log base 2.
You said log base 2 of 2.
Yeah, 2 to the x. That brings down the x. So
Here, though, you're actually done, right? Because now you can use change of base.
you reach the same exact thing the other way too.
Because I had natural log of 12 over 2, which became natural log of 10. Yeah. Thank you, Michael.
So I can do it that way?
Yes, because you're still good, because you got natural log of 10, which is what I had when I erased all this. I was like, why aren't they matching?
Yeah.
I did. I had ln of 10, which is 12 minus 2. Because remember, rule for division is you can take top minus bottom.
So the first time I got it right, you got it wrong. How about that?
However, what's super funny is he actually caught this. I didn't hear you arguing.
So Pluto and I both got
You were actually so. We're just done. This one's a little trickier than the last one because you can't just auto natural log both sides. It's like the square roots when I was like, you can't square both sides till the square root is isolated. You don't want to ln both sides till the e is isolated. So you want to subtract over your 5, giving e to the x equals 55 before you ln both sides. So now when you ln both sides, x is a nice, lovely natural log of 55. And then I'm going to put everything back up that was already up there. Okay, population P of a city is given by the following expression, where T is 1990. According to this model, when will the population reach 150,000? So that 150,000 is not going in for T. T is time in years. It is going in for P. This is like what we kind of touched on yesterday. You're going to divide out the 105, 300 first. So as a fraction, this reduces to 500 over 351. So now what do I want to do? Yeah, ln both sides. How do you solve for t?
Divide by 0.015.
Exactly, divide by 0.015. So that's like 200 times the natural log of 500 over 351, which is 23.58 that represents the number of years since 1990. So if we needed to know a year, you would take that 23.5, add it to 1990, and we get approximately 2013. And then because of the 0.58, those represent months. So it'd be July of 2013, because you're about 60% of the way through the calendar year, which is a little over half. So like month 7. Or you could take 0.58 times 12 and get 7 too. All right, so let me go through the 2 homework assignments I had mapped out and kind of work them so that they're fully together. You may take your 5-minute break.